I wanted to do more experiments with fluorescence. Say, when a substance lights up, when it is bombarded, in a certain way bombarded, with ultraviolet light. And well, I told a little bit about this in my preceding video anyway. In the past I've made, say, more experiments with ultraviolet detectors, ultraviolet, say, LEDs. And the issue with these ultraviolet LEDs is that they need a very, very precise current. Thus it means an effect that applies to all light emitting diodes, that they need a constant current source. That can be done in many ways, via a chip, via a transistor, or whatever, etc. I don't know. I do know what that's all about. Here are, say, ultraviolet detectors, and I'm surely going to give the link in the text box of this video. This is that earlier published circuit here. It's an ultraviolet radiator. It works on two frequencies, 400 nanometers, and here 278 up to 280 nanometers. So a dual ultraviolet source, but of course it's important. This is a very weak source, but you can do experiments with it, and that's the aim, also the aim of this video. So that was the history. Let's go now to the circuit that I'm working on, and it was more or less in a definite way developed. That's here. This is the schematic. And let me tell something about it. There are two ultraviolet LEDs here. They are supplied via a power supply, of course. They need a DC voltage on their two electrodes, but their current is very critical, and that also means the maximum current must not be too high, because they directly burn out. So when you want to make such a circuit, there are a few important things to tell. Go to the data sheet of the ultraviolet LED that you want to supply with voltage and current. Current is, say, the key. Anyway, look at the data sheet, study the maximum current, measure the current and the voltage, the voltage parallel to the ultraviolet LED here. In my case it is this type, but of course there are other ultraviolet LEDs. Study the data sheet for the properties. This is a useful test circuit, that's what I wanted to tell, and the barrier voltage is in this case 1.28 volts. And by purpose I have connected here my voltmeter parallel to these two ultraviolet LEDs, and of course there are here two protective diodes. Do they have a job? Yes, they have in a certain way a job. I've tested it, and even on higher voltages. These two normal silicon diodes, by the way, they have a voltage drop of each of 0.7 to 0.8 volt, and when the voltage gets too high they break down and protect in a certain way the ultraviolet LEDs. But that protection is in a little bit way moderate anyway. So again, the question, why do you need such a big circuit with so much components? It was tested, and the whole idea is that we and I don't want to damage these LEDs by a too high supply current anyway. So this is a resistor that helps in that respect. There is here a stabilized voltage supply that helps in that respect. That means that you can add here 12 volt or higher, but in general the ultraviolet LEDs will not burn out due to all these protective measures. The diodes here and say the stabilized voltage here. Of course, when we say change the output voltage here a little bit, the stabilized output voltage, that's what I mean, and you can do that here by adding here one or more normal silicon diodes in the row between the base and the minus. The current will change, so the maximum current, that's what I mean, that the say the ultraviolet LEDs receive changes somewhat. Let me demonstrate it. Here is the test circuit. Here is the Zener diode, by the way, here. And these are the normal silicon diodes in the same configuration from the base of the transistor, the BD13992 minus. Here are the ultraviolet LEDs, and here we look at the voltage that is applied to the ultraviolet LEDs, and here we look at the current. The maximum current according to the datasheet is 300 milliampere. I want to stay on the safe side, so I adapted these two diodes here. I use these two diodes to limit the maximum current. Has everything to do with Ohm's law, etc., etc. It means, say, that you change here the voltage drop between the base and the minus. That means that also the output voltage is stabilized to another value. Well, perhaps it's a little bit complicated, but much more info about how this works is on my YouTube channel. I'm going to add now voltage to the circuit here out of my normal power supply. Let's see what happens. Slowly build up that voltage. Let me go to, say, the voltage where it was all developed for. We now on, say, 4 volt, 5 volt, don't see any current flowing. That's logical. We go to the right supply voltage. That's 12 volts. And I don't see anything happen. Well, I don't know why. Well, there's no connection between the meter, etc. So I don't want to spoil my video. Make a direct connection. Well, here it is what it's all about. Here we have the current that's flowing now in the circuit. It's 250 milliampere approximately. The voltage drop parallel to the two ultraviolet LEDs is 1.24 volts. 12 volts. And I will switch out all the lights now. And especially to look to the, say, ultraviolet LEDs. They are at this moment quite fierce. I think it's good enough. It is of course invisible light, but because I used say this camera with an electronic chip inside, that electronic chip can pick up that light, and the human eye cannot pick up that light. But that's also a very good idea to be used when you want to do these experiments. Use your camera and say, look at the light that the circuit that you are developing, how much light there is emitted. And I now want to say, give the whole circuit much more voltage. Now it's 12 volts. I now give it 20 volts, and there is no change in the emission of the two ultraviolet diodes. Perhaps a little bit, but anyway, a little bit more energy is strayed out. Well, that was more or less all to tell. Thanks for watching at first. This is, say, a safe way, and that's the whole aim of this video, a safe way to get these ultraviolet diodes working. So now we have here a higher current. I think it's between the limits. So now we are on 20 volts. I go back to 12 volts. Of course, nothing is perfect, but this is safe way to use this ultraviolet diodes on a voltage of 12 volt, between 12 and say 14 volts. That was also the aim when I wanted to develop it. Here again the voltage drop parallel to these two ultraviolet diodes. The schematic again, and of course when you want to develop such a circuit for other ultraviolet diodes, it could be that you have to adapt it. So in that case, look at first at the data sheet, especially look at the maximum current that these ultraviolet diodes need. Measure the voltage parallel to the UV diodes. Measure the current. They must not exceed the data sheet, and then afterwards you can search for a good circuit that in a certain way has the property of a constant voltage, like it's done here, or a constant current. All LEDs in general have to be supplied by a constant current source. There's a video of that on my YouTube channel. I don't want to go now into that subject, but anyway, this is more or less a quite good circuit. Say when you want to make a small beam of ultraviolet light, ultraviolet frequencies, and then here it is on between 920 and 1000 nanometers. That's a very high frequency. Thanks for watching.